Welcome to our final podcast of Chapter 16, which is all about reaction mechanisms. So the definition of a reaction mechanism is some sort of a series of steps, usually, by which a reaction takes place. So a lot of times we'll write out a reaction. Here we've got our carbon monoxide, nitrogen dioxide reaction that we've seen at some of our other podcasts we've gone along. And so, yeah, that happens directly like that. We have that collision take place, and this reaction occurs at high temperatures. Right? But if we're at lower temperatures, it's not this reaction doesn't take place. It does. It just happens to happen over several steps. Remember, we probably talked about that in Chem 1, where when we have multiple steps together, that means that we're coupling reactions together in order to get an overall reaction. The overall reaction is still going to look the same. It just happens over a few different steps. So here we are at lower temperatures. We have our nitrogen dioxide, but it's colliding, notice, with another nitrogen dioxide to produce nitrogen trioxide and nitrogen monoxide. All right, then we have carbon monoxide is going to collide with nitrogen trioxide to produce carbon dioxide and nitrogen dioxide. Okay, so when these two reactions, though, what we do when we couple reactions, remember, is that we are going to cancel anything that is a reactant and a product somewhere along the line. So if you notice, we have nitrogen trioxide as a product in step 1, but it's a reactant in step 2. So it's going to cancel. And here we have NO2 as a reactant in step 1, but a product in the final step. Those are going to cancel. And so notice that when we add everything together, we add these up overall, we still get this exact same overall reaction. Carbon monoxide plus our nitrogen dioxide producing carbon dioxide and nitrogen monoxide. And so the overall reaction is the same, it's just how we got there was different. That's what we mean by a reaction mechanism, right? It takes place in a different way than it does at the high temperature there in this case. Well, in the previous slide, we saw that, sometimes our overall reactions happen to take place over several steps. And when they do take place over several steps, then we call those several steps elementary reactions. And so when we have elementary reactions, we can describe each one of them by something that we call the molecularity. Right? And that is how many molecules are there on our reactant side. So we can have a unimolecular reaction, all right? And so this doesn't mean so we could have a unimolecular reaction where it could be, say, 2 of A becoming, say, B plus C or something like that. That still means there's only one molecule. We're only talking about each one of them individually over there. So a decomposition reaction is unimolecular. Bimolecular reactions is where we have two things. Again, that could be 2A plus B, C plus D or something like that. And then we could have termolecular reactions, and those are rare, and that's where we have 3 different things that are on our reactant side coming together to form our products. Why are termolecular reactions really rare? Well, because the sterics of having 3 things collide all at the exact same moment, all with the right amount of energy, and all with the right sterics, the odds of that are so rare that they don't happen very often. All right, so we're going to work on, looking at being able to count unimolecular, bimolecular, and termolecular pretty soon. The other thing, because this is a rate equation chapter, when we're talking about rates of things, when we have a mechanism, which means that we have multiple steps, sometimes, those steps are going to happen at different speeds than one another. And so often one of those steps is going to be the slowest step. Whichever one is going to be our slowest step, we're going to call the rate determining step. Meaning that in order for us to determine the rate of our reaction, we don't need to know the rate of every individual step along the way. We only need to know the rate of the slowest one. We're going to do a real world sort of an example of that. In nature, it's going to be even more vastly obvious. but just know that when we do this, the slowest step is what's going to determine our overall rate of reaction. So let's do a sample problem, and in this case it wants us to say, all right, the decomposition of nitrile chloride is believed to occur by, okay, we've got this mechanism, these two steps. And so it wants us to find the overall reaction. Well, remember that to find the overall reaction, we have to cancel out anything that we see as both reactants and products, and then write down whatever is left over. So I have NO2Cl, I have nitrile chloride in step 1 and nitrile chloride in step 2. So what that means is that I'm going to have 2 nitrile chlorides as my reactants. They're going to decompose to produce, all right, NO2, but there's 1 in step 1 and 1 in step 2, so there's 2 NO2s. And then we also have a chlorine gas, like so. So that's our overall reaction. Then part B asks, what is the molecularity of each of the elementary steps? So in number 1, unimolecular, right, because the only thing there is nitrile chloride. And in the second elementary step, there's a chlorine and a nitrile chloride, bimolecular. All right, lastly, part C of our problem asks, what rate law is predicted by this mechanism? If the first step is rate determining, all right, so if the first step is rate determining, then the rate of our reaction is equal to K times, all right, NO2Cl, that's the only reactant, raised to some power. Right, so when it says this, right, when we want the rate law, all we have to do is the one for the rate determining step. We don't have to worry about the second step in there because it's going to be much faster. Let's do my real world example here where we have 3 people grading an exam. Person A takes 10 seconds grading question 1. They hand it off to person B, who spends 15 seconds doing question 2. And then they hand it off to person C, who takes 5 minutes to grade question 3. It says the rate at which the exam is graded is, all right, so the rate is going to be exams per, say, let's do this in seconds. All right, so person 1 spends 10 seconds. So here we have, sorry, 1 exam. Person 1 takes 10 seconds, person 2 takes 15 seconds, and person 3 takes 5 minutes, which is 300 seconds, which is going to be a rate of 0.00308 exams per second. All right, the next one's asked the rate at which grader C graded is, all right, well, they grade 1 exam per 300 seconds, which is a rate of 0.00333 exams per second. All right, and so what we're going to say here is like these numbers are approximately equal. They're not great, right, but they're good enough for government work in our opinion, and so it's just a heck of a lot easier to go ahead and say the rate of our reaction is just going to be the rate of person C, as opposed to having to put in every single step along the way. We just do it for the slowest step when we calculate these. All right, lastly, we can see then by a figure, right? When we look at a figure, the slowest step is going to have the highest or the largest activation energy. The reason for that is because it's the hardest one to overcome, right? The larger the activation energy, the slower the rate of our reaction is. And so the bigger that is, then that's going to be our rate determining step. So we're looking at a figure. It's easy for us to determine the rate determining step by looking at which one has the highest activation energy there. All right, that ends chapter 16 podcast. So good luck working on problems. If you have any questions, please don't hesitate to let me know. See you in chapter 17.